Okay, so these are the lecture notes, or my explanation of the lecture notes, lecture number 3, which is, okay, this part, sorry. Spectral analysis, Fourier transform. This is the part I'm going to talk about right now. We'll talk about linear filters next. Hopefully we'll do both of them today. So let's get started with spectral analysis in Fourier transform. First thing to kind of understand or keep in mind that we are dealing with digital signals, and in order to do spectral analysis, of course, there are many ways. When you normally start studying Fourier transforms in electrical engineering, I would say you deal with analog signals or continuous signals, and then all your transforms are basically continuous in time, continuous in frequency. You use integrals as the transform. We will not do this for several reasons. First, even though maybe the math makes sense to start from continuous functions and go to discrete sequences, and then you kind of see this relation in somehow more general way, is not really needed for what we're going to talk about. And practically, since we're dealing with digital or digitized sound, this is the stuff you will be dealing with, and this is the assignment about DFT. It all has to do with so-called sound vectors. And the reason we move from waveform to vector is because we think about a waveform as a continuous thing and a vector as a sample of that waveform. So let's talk a little bit about sampling, because even this is kind of a super important part in digital signal processing that we're going to skip, except for some basic facts that I want you kind of to keep in mind. We will not provide the proofs, but the important concept in sampling a signal, or the basic question that it's sometimes called the Shannon sampling theorem, the Nyquist sampling theorem, it deals with the question of how many samples you need to take, which means like how fast, or what are the milliseconds, or what rate you need to sample a continuous signal in order to be able to reconstruct it or preserve the signal once you go back from the digital to analog. So if you think about the process of processing sound in the computer is going from analog to digital, or ADC, then once you did your processing in the digital domain, you go back and you want to play the sound, so you have to go back to continuous. You do DAC, digital to analog. It doesn't mean that you can do anything. I mean, like, you do need to know something about the signal, the nature of the signal, the analog signal, in order to be able to go and represent it in a lossless way, or in a way that could be reconstructed back from the digital domain to the analog domain. So there's one theorem that I want you to keep in mind, and some of you probably have heard about this, or at least are aware of the fact that every sound file has a sampling frequency. So what is the sampling frequency? Well, this is really the rate that, the spacing between these red bars, or the red dots, that capture the signal. The number of these samples a second is called the sampling frequency. And here I kind of use the Fs as the sampling frequency. So you can see that if you have enough samples every period, you just visually, can imagine that you can reconstruct the top waveform from the samples. Of course, you need some sort of interpolation. So the whole theory, the sampling theory, gives you the optimal interpolation functions that will actually recover your frequency components. Now, as this waveform, the blue waveform, becomes faster and faster, which means more and more periods, or the frequency goes up, you hit a point where you basically have 2 samples per period. Of course, it doesn't have to be synchronized with, with the peaks and the valleys in the waveform anywhere, but there's still, have at least 2 points in every period of a sine wave. So the theory of sampling tells us that this is the maximal frequency that you can then recover back from the samples. And this is called Nyquist frequency. And as I said, because you need 2 samples per per the physical waveform period, that means that the Nyquist frequency, or the frequency of the blue wave, okay, that's the physical frequency, okay, the highest one, the highest frequency you can reconstruct in the real world, in the analog world, is half of the frequency of these samples, okay? So if you think about the distance between this as the sampling frequency, the frequency of the blue wave is double, right? Because you have two samples per period. So what happens if you have frequencies that are higher than the Nyquist frequency? So if you're in your analog, in your real world signal, you might have, or it depends what you set up. I mean, usually you can define what sampling frequency you want to use. But let's say you decided that you're sampling at 8 kilohertz, 8,000 samples a second. So the Nyquist frequency will be 4 kilohertz, or half of the 8. What happens if your signal has frequency components which are higher than 4 kilohertz, which is, very natural. I mean, most of our speech audio signals have frequencies. We perceive frequencies up to 20,000 hertz. We can hear them. We mentioned the idea that we perceive pitch only in the lower frequencies up to a couple of thousand of hertz. But beyond that, we perceive them as timbre, as color, but we still hear these frequencies. Some animals can hear beyond the ultrasonic frequencies, above 20,000 hertz. Usually the energy of the signal goes down with frequency, but nevertheless, if you go back to the example of the 8 kilohertz sampling rate or the 4 kilohertz Nyquist frequency, your audio signal might have something which is higher than 4,000. Let's say you have a signal at 5,000 hertz. What happens to it? So this is the last graph. It shows you that if this is your audio signal, okay, your waveform, and the period, okay, or the frequency is higher than the Nyquist frequency, and you still sample it the same way, you basically, when you want to reconstruct a new wave from the red dots, you have an ambiguity, because these red dots, I mean, this example is designed in I think visually such a good way that you can see that these red dots are the same on the top and the bottom. So actually, if you would reconstruct a signal from these red dots, most likely you will reconstruct this frequency, or not most likely. I mean, the interpolation function that you would use to recreate a blue line from the red dots, even though your blue line here is much faster frequency, you will reconstruct the blue line on the top, which will be a lower frequency. So mathematically, this effect is called aliasing. Why aliasing? Well, it's more like a reflection. If you think about frequencies increasing from very low frequency up to Nyquist frequency, and you're able to reconstruct them perfectly, if your frequency keeps going up in terms of the blue line, the physical frequency, what happens when you reconstruct them, you kind of go back down. You actually reconstruct lower and lower frequencies. It's kind of reflected around the Nyquist frequency. It's a very fun experiment if you want to do this either in Python or even in Audacity. You create a chirp, you set your sampling frequency to some low frequency range, and you see that basically, even though mathematically it tries to generate frequencies which are higher and higher, just the fact that you set the sampling frequency, you will hear it on going up, hitting the Nyquist frequency, and going down. And actually, if you keep on going up and down, it will keep bouncing to zero and to Nyquist and zero and Nyquist. So once you set your sampling frequency, basically you live in the physical world, or if you want to go out of the digital world to the physical world, you live in a domain of frequencies which are between the zero and the Nyquist. And to avoid aliasing, you actually have to put some kind of a filter, a low-pass filter that will remove all the high frequencies. There are some other ways to kind of try to deal with this, with these issues. One of them is really sampling in very high rates, and just you usually don't have acoustic energy in very high frequencies, or if there is aliasing, it happens very high. Whatever solution, I mean, technically you choose, we will assume that we have a sampling frequency and that we don't have any frequency components in the original signal, which are higher than Nyquist. Okay, so having said that, we need to keep the term of the sampling frequency in mind, because everything now, once it's in the digital domain, will translate back to the acoustic domain in reference to the sampling frequency. So one more thing that we need kind of to use or keep in mind once we think about the Fourier transform, that's kind of the mathematical representation, is that what we try to do is decompose the signal into its pure sine waves or pure phasors, if you want, because we spoke all the time about sine wave, but you can talk about cosine. So sine and cosine, I mean, they're basically all look the same, except for they're kind of shifted by 90 degrees, by pi over 2. Now, if we want to capture the period and we don't really care where exactly that wave started, we kind of need to know the phase. We cannot just rely on a sine wave or a cosine wave. We need everything in between. So the nice trick is that actually, if you use both sine and cosine, you can always mix them. And I will not show the math here, but you can try to work out the geometry, the trigonometry of sine and cosine. You can see that by mixing sine and cosine in ways that, if their amplitudes, the root square of them is 1, is equivalent to creating a sine wave or a cosine wave with a shifted phase. So what basically I'm saying, if you take two sine waves, like a sine wave and cosine wave, slightly with different phases, you sum them up, you still have a signal of the same frequency, which is just shifted. Why I'm mentioning this, because we need then the sine and the cosine element to capture frequencies regardless of their time, and the phase will be in the relation between sine and cosine. So mathematically, the easiest way to do this, of course, we can work separately with sine and cosine, and this is one way to do this. But if we want to kind of use some more elegant math, assuming that the complex numbers, feel comfortable with them and you enjoy the elegance of that representation, we will use, instead of sine and cosine, we'll use so-called complex phasor. Complex phasor is basically this. Okay, this is the expression of a complex phasor. If you're not confident about what it means, I would ask you to kind of refresh your calculus, the complex numbers part. But you can see that, if we have a unit circle, okay, and this is the imaginary, this is the real, every point here can be projected to cosine of an angle and the sine of an angle, right? So the sine of the angle is this part, okay? So this is the sine, this is the cosine, and this point is the exponent. So exponent, the complex exponent is actually translated into cosine, whatever the angle, exponent of I is the square root of -1. So exponent of I, gamma is the angle, equals practically, not practically, that equals exactly to the cosine gamma plus I sine gamma. If you want to prove why exponent with a complex number in the power is cosine and sine, cosine plus the imaginary of a sine, I think the best way to try to prove this is actually look up the Taylor series expansion of an exponent of a sine and cosine, and you actually see that they combine together. There are other ways to prove this, but I know it might kind of look strange why e to the power of some exponent becomes sine and cosine, but that's how it works. So why I'm mentioning the phasor, because we will use this expression to represent frequencies. We will not use sine and cosine, we'll use e to the power of something. So what we normally do, because we're going to deal with discrete signals, okay, we're going to divide our unit circle into some number of steps. And what we'll do, we'll have a window, we'll have a fixed number of samples that will be the size of our sound vector. Let's say we had n equals 8. That means that we basically kind of subdivide this circle into 8 points. We cut the pizza into 8 slices. And then as we go and jump by, in this case would be 45 degrees, right? Or pi over 4. So if n is 8, you'll have pi over 4. So every time we do one step, okay? So let's say this is our basic step. And then let's say we take the first one. When you take the second one, we just multiply this by 2, or take this as a power of 2. will reach here and here and here, and it will keep on rolling around. And this is kind of a demonstration. This is this Wn power of 0, Wn power of 1, Wn to the power of 2, 3, 4, 5, 6, 7, and 8. We come back here. And these will be now basically values. So these are kind of the samples. Instead of sampling in sine and cosine, these will be numbers, complex numbers. You can, again, as I mentioned, if you feel more comfortable, you can think about it as a vector of sine or the vector of cosine samples plus the I or minus j. There is kind of ambiguity notation here. I here is j here. I mean, they both represent square root of -1. And if we do that, okay, we will basically, and in Fourier transform, we use the minus, so we're actually going the other way. But bear with me with this kind of little ambiguity here, or inconsistency in notation. What the point I want to make is that we basically move around this circle, which is equivalent, or sample this circle, which is equivalent to having a vector of cosine samples at certain phases or certain angles, okay, and a sample of I times sine sampled at these phases. So what we do basically when we do Fourier transform, as strange as it might seem, we create a matrix. And this matrix kind of are the powers of that Wn. So Wn to the power of 0, all of that will be these samples. At the power of 1, we actually move by 45 degrees. At the power of 2, we move by 90 degrees. At the power of 3, we move by 19 plus 45, 135 degrees, and so on. Okay, so these are really just numbers, complex numbers that create this matrix. This will be our time sample. We have 8 time samples, and we do matrix multiplication. We multiply this by this. Okay, we get this number. Now, these are real values. These are complex values. So this is a complex number. Okay, then we multiply this by this. Okay, we get this number, which is a complex number. That's basically what a DFT matrix is. This is what you have to kind of write down mathematically in your assignment. And if you want to look at this in a more kind of formal notation, we mentioned this idea that we have this Wn, okay, as our basic element, and then we take powers of the Wn. And the convention in Fourier transform is that actually, if you go from time to frequency, okay, we go from real to complex. We go actually down on the circle. We go in the other direction. We go with the minus here, and this, series expansion or explicit form of this this equation, this explicit form of writing what xk is totally equivalent to multiplying the vector x by a matrix D. All it gives you is the case, our the column here, if we index the column by k, so column number k, the value, okay, at index k on the column will be this row, case row, times all of these n's. So the summation is over n. So this will be here. Check out the math. That's kind of the matrix, the algebra representation. Really, there is not much more than really kind of looking into this, seeing what it means, and understanding that it's just a transform. It's a transform, a special type of transform that takes vector from, maybe the only confusing part is that it takes vector in an n-dimensional real space and translate this to a vector in an n-dimensional complex space, but they're the same dimension. And then you can go back, and this is really one of the major advantages of of this representation is that you take the same matrix, okay, and you just, well, it needs to be an inverse, but so it happens that the inverse of this matrix is just a conjugate of the original matrix. So you basically have this Wn, instead of the original Wn had a minus here, and now you take Wn with a minus, so what we will have is basically an exponent with a plus. So this is kind of the same matrix going just backwards. And if you now plug in here your Fourier coefficients, the complex numbers, you'll get back to your original sound wave vector. I hope it kind of demystified the concept of Fourier transform in the digital domain or in sampled fixed size vectors. So here are the main takeaway points. I would recommend people who are interested and really outside of the class, because we have so much other material to move forward, but kind of if you feel a little kind of curious about more physical insights about Fourier analysis and transform, consider the original, or where it started from, which was in the continuous domain. So same logic applies to the continuous domain. You have a signal, an analog signal, where t would be your continuous time vector. So this is basically a function, a waveform. And then you do a Fourier transform. In that case, you use an integral, and the integral is from minus infinity to plus infinity. So that's a very kind of different type of calculus. So here you use integral calculus. Here we use algebra. But if you go there, you end up with a function where f is a continuous. This is your frequency value, and x will be a complex function. Both in the analog and in the digital domain, you can think about this as a change of representation. But I mean, I think once you think about this as a matrix operation, it's really very evident that this is just taking a change or change of, sorry, it's not or, it's change of representation. And in the DFT, you have both discrete time and discrete frequency. So while n would be samples in time, k would be specific discrete samples in the frequency domain. And really to understand the frequency domain, we then have to go back to that idea of sampling frequency and try to relate the index k to physical frequency. Same way we have to relate n, which is just a number 1, 2, 3, 4, to seconds. Okay, so n and k are just indices. Okay, in the real world, n has meaning of time once you know your sampling frequency, and also k will have a meaning of frequency once you know the sampling frequency. But I mean, in sort of the abstract algebraic form, n and k are just a set of integers. So you have a sound vector of size n. It results in n spectral bins or samples. And from here, it kind of, I think, intuitively clear, maybe mathematically does require a little bit more proof. So, trying to take a whole signal processing, digital signal processing class, which usually comes after you take linear systems and then learn about Fourier analysis, and then you go into sampling, and then you go into DSP. It's like almost, I would say, definitely a year of electrical engineering in 5 minutes. But that's allow you to feel comfortable with operating with DFTs. So what you have is you have a frequency resolution of Fs divided by n. Why? Because our sampling frequency, okay, is actually double than the frequency we are representing in the real world. And then you think about this, division of sampling frequency to n. Why we divided by n and not half of the sampling frequency by n? Because we need both sine and cosine, and what you get is, and this is where the math is, skipping a lot of this, is that because xn is real, xk will be symmetric. The Nyquist will basically get some kind of strange representation where we only have, in terms of at least the amplitudes, not the phases, we have the same amplitude going to Nyquist and going above it. But you get total of n samples. So we call this a frequency resolution of Fs divided by n, So just keep this in mind, okay? That this is kind of, once we need to go back from K to Hertz, that's what you do. You take Fs divided by N and multiply this by K, and this is the frequency you would represent. You just need to understand where to look how to look up the Ks. And once you hit above Nyquist, you get that aliasing. You get sort of like higher frequencies, but they're basically the same frequency, just going back to zero. So in practice, what we have is only half, because the amplitudes are symmetric. You get n over 2 amplitudes, okay, of xk. So here we take an absolute of the complex number, and we have phases. And the phase, remind yourself of, how you calculate the phase in a complex number. It's really the imaginary of xk, okay, divided by real, or the tangents. So this is like, yeah, oh, I'm horrible with the names in English. Whichever is the hypotenuse. Look at the triangle. Okay, sorry about that. And the perpendicular part versus the one that is lying down. This is if you take an arctangents of this. So it's something. So phase equals. I'll have to correct the slide. Too many typos. Here's an off. Here, phase equals A tan, or inverse tangents of, and here are parentheses, of imaginary divided by real. So what are the functions of the libraries that do that? You have FFT, which is fast Fourier transform. Just to mention the name, why it's called fast, because it's a very specific implementation of the Fourier transform that saves you a lot of time from doing really matrix multiplication by doing these kind of a butterfly flip-flop kind of calculations. We will not cover into that, but this really made a big revolution in digital signal processing, because FFT became very fast. It became so fast that you actually moved from doing filters, and we'll talk about filters later, from doing them in the traditional time domain to going through FFTs and doing everything in the frequency domain. But fast Fourier transform for us is just the name of an algorithm that makes the Fourier analysis fast. It has a small caveat that to use this algorithm, your vectors need to be power of 2. This is why so much in signal processing you use buffers of 32, 64, 128, 512, 1024, whatever. This is really why these kind of strange numbers come out in audio signal processing, is because if this is the buffer, this is the sample, the sound vector you want to work with, you'll benefit from the advantages of using the fast Fourier transform. Otherwise, you have to do the slow Fourier analysis. So if we take here, here actually we don't use a nice number. We take 1,000 samples of some sound vector. This is your sound already represented as samples. We take some window. We take samples from, just for the sake of the example, from 15,000 and 101st sample to 1,600 and 100. So we have total of 1,000 samples here. Okay, and now we run the 1,000 samples through a Fourier transform. Okay, what we will get, okay, we'll get actually 1,000 complex values. Okay, because we started with x lengths of 1,000. Our n, the sound vector, was 1,000. Our capital X, the Fourier coefficients, will be also size of 1,000. But as we said, they actually are symmetric in the amplitudes. Okay, so we usually do not want to plot it. If we plotted the whole 1,000 samples, we'll either see this, depending how you calculate, you give your index, you will either see this pattern and then it being reflected, so it will start low and we'll have at the right end the same thing, basically a mirror reflected here. In some cases, it really depends on how you organize your indices. People tend to make the reflection around 0, and you'll have basically the flipped here. You have a small peak here, a larger peak here, and it goes down like this. But because it's redundant, we just plot 500 of them, and these are the amplitudes. So these are the amplitudes of the different frequency components. So this graph is what we would normally call spectral analysis, but we neglect this phase, which is this inverse tangent of this complex number xk, it has to be included in order to do the inverse, exact inverse operation. So one of the topics we'll deal with is because this is very problematic data. Yeah, not only it doesn't look as good, it's very sensitive. It's sensitive to time shifts, it's sensitive to little errors in the signal. And when we want to generate, we kind of have a good idea how this and where this comes from, but the relations between the phases, basically how the different frequencies synchronize in terms of being slightly shifted against each other. You know, you add the reverb, and if you have a great reverb that basically it's a kind of room resonance, let's say, and it's very nice, it doesn't change the amplitudes, what it'll do, it'll shuffle the phases, and you perceive it, but you know the amplitudes look pretty robust. You do a chorus effect. Basically, you multiply some instruments with little delays. You still get kind of the same overall frequency shape, and this is immediately totally distorted. So we are sensitive to phase, but in some kind of a remote way, I would say. We perceive space, we perceive color, we perceive size, basically kind of like the idea that it's not a single source, multiple sources. But for most purposes, we kind of tend to ignore the phase. And if you just have the same signal and you just shift it in time, you slightly change the phase. For a very dry and clean signal, you don't really notice the phase. So people tend to say that we don't hear the phase. We do hear phases, but we hear them as something else. We hear them as perception of space. We hear them as perception of the size of, you know, how many duplicates of an instrument exist. We perceive them also in terms of sound quality. So the phase is important, but we will ignore this for most of our discussion here. So if you look forward, go forward through the syllabus, you will see that we talk about algorithms that will create a synthetic phase, the Griffith-Lemma algorithm, for example, that will come up with some kind of reasonable phase that will allow us to reconstruct the sound vector, the sound itself, from a sequence of Fourier analysis that do not have the phase. Now, why do we care? I mean, I said if we don't care about the phase, why not put just any random phase? So we'll talk about this. I mean, yes, you definitely can just put some random phase. It will reconstruct one frame. But the next thing we're going to talk about is so-called short-time Fourier transform. And this is what we do. We have a sequence of short-time transforms, because this is what the spectrogram is. So now we kind of make this big shift, and we do this at the point where I was talking about phase. And the reason that we do need to have some attention to phase is because now we have kind of a strange generalization or extension of, you know, the one frame DFT applying a matrix to a fixed length sound vector. And this is that, you know, we have very long sound signals, right? You can have a recording of many seconds, minutes, if not hours. You don't want to take this whole recording, create this huge vector of thousands of, not thousands, of millions of samples, create this million by million matrix and analyze all the frequencies. Not that it's not doable, it's just that the meaning of frequency in some sense is lost. Why? Well, the frequency is there as a transformation, but really what we want to find out when we do the Fourier transform is this, and for me the most intuitive is really to think about this as a relation between frequencies or the analysis and, let's say, the piano roll, the symbolic representation in music, but that applies actually to anything. We hear frequencies, but these frequencies change in time. Now the definition itself of frequency is just taking a block of signal over some kind of a window in time and just changing the transformation. So once we do that, we do get kind of a frequency decomposition of that signal, but we will not see the fact that there might be something that we would perceive as a change in time. So if you take, a whole melody and just take this whole sequence of notes as your sound vector, and you make a Fourier transform of that, you will see now kind of a frequency decomposition of the whole signal. And then you can invert back and get back the original signal. But when you look at the contents of in the frequency domain, the time will be kind of in a strange way encoded in the relations in these phases, and you will not be able to see that here was one note playing, here was another note playing. So this is when the phase really has so much information that we don't know how to interpret. So to avoid this, what we really do is we take short enough windows in time, and we do separate DFT analysis of each one. And this is called the short time Fourier transform. So it's a sequence of DFTs, and each one is done on a sliding window in time. What I mean by window, if this is kind of my poor attempt to draw waveform here, okay, as time, these little kind of arches on top are the windows. What we mean by window, we basically open kind of the shutter, okay? It's like, I don't know if you want to think about this as photography or film. You open the shutter, you take a snapshot of your waveform, and then time keeps going, and you take another snapshot and take another snapshot. So these are your shutter openings, and they can overlap actually in time in audio, unlike let's say in the old cameras that either close or open. Here you basically kind of have an overlap between these samples, and we'll talk about exactly how to design these windows. We will not talk about them because that's again a whole topic and expertise of electrical engineers. But the idea here is that we basically take some kind of a snapshot, we isolate a part of the signal from the rest of it, and that becomes now a finite dimensional sound vector. And then we run a DFT on that. So what we'll have now is a two-dimensional output, and this is written here. So this is our signal now, n, x of n, but the n now runs not from 0 to that capital N, which is just one sound buffer. It goes from -infinity to infinity. This is our whole sound. I mean, this is that long wavy waveform is represented here, if you want, as a vector. Really long one, but you extract a round time tau. So tau is usually representing either the center or the beginning of that window. So this window is moving, and you index the time of that window by tau. So this is a shifting of a basic kind of a window waveform. And the easiest way to think about this is really just a square window, zeros and one, to some extent n, and then zero. So every time you shift that window by tau, and you extract that segment from your original signal. So what we end up having is really just a small segment of xn. We run DFT on that, and that will give us now two results. You have the original DFT with index k, the frequencies. So to keep in mind or remember where in time we took that window, so this is tau. So this is what we get as a two-dimensional matrix, x of k and tau. So it localizes the signal both in frequency and in time. And this is what a spectrogram is. Okay, so if you run spectrogram, I think here I was using still a notation from MATLAB. So you have a spectrogram. If you look in Librosa or some Python packages, it might be called spectrogram or something else. But the term, the mathematical term, the engineering term is spectrogram. And again, it takes your signal, which can be as long as you want. You have to specify the size of the FFT. You want to have the sampling frequency if you really want to understand. It's usually for plotting purposes, kind of to put this in physical terms. Okay, if you don't do anything, it will just take some number like 1, and everything will be between 0 and 1. You have to specify the type of the window that you're using, this W, and actually the analysis is sensitive to types of windows. And I kind of mentioned that we will skip that, but just be aware of the fact that there are different windows. And the boxcar, or just the 1s and 0 window, is not the ideal window. Usually we have kind of a nice tapered window and we'll talk about this when we talk about a reconstruction of the signal from STFT. And there, relation between those start mattering. And if we have these windows moving not by one sample but by skips, we have to provide some kind of an overlap or non-overlap. It depends on the implementation, but something that tells us by how many samples in time we shift the window every time. You know, the idea that you can move the windows in overlapping fashion is important. This is pretty much concludes all the math about the spectrogram. And just to summarize everything together, is that the DFT itself is just a matrix multiplication on a finite length vector of samples of your sound. And then the short-time Fourier transform takes a much longer sound vector, extracts a portion of it by multiplying this with a window, and then applies a DFT operation to each one of these extracted and segmented portions of your original sound waveform. And then you represent this as a two-dimensional matrix, where one dimension will be the frequency and the other one is the time where you did the analysis. Now, one other concept to keep in mind, because you change the NFFT or change the window size, okay? And in theory, they could be not the same number. The way I presented this, the NFFT as a number will be the same as the length of the window, but the implementations allow you to have different numbers of NFFTs, and it makes sense only if you want to have more NFFT than the length of the window. Why would you want to do this? Well, basically what happens there, let's say you take a window of 512, and naturally you will have an NFFT of 512, and this is the matrix that we handle. For graphical purposes, for the way you kind of look at the frequencies, you might want artificially to increase the NFFT, let's say 2024 or 2048, just have much more frequency samples. Are there real frequencies at that resolution? No, it's just that the interpolation, the way the FFT works, will look much nicer to us in the eye. And what the program will do, it will basically take your window and pad it with zeros until it fits the NFFT number. So this is kind of a mathematical trick. It has to be explained why it actually works. I mean, it works just that, I can take a window, pad it with zeros, and then apply an FFT. The matrix, everything is fine, but kind of like why it makes sense as a representation of the signal, or the fact that we actually don't see any new frequencies, it just makes a more smooth visual effect. But if you play with this and you get that visual effect, you will notice that it seems to improve kind of the quality of the analysis, but all it does, it kind of just makes a less boxy picture. But having said that, let's assume for a moment that we always keep NFFT as a number and window as a vector of samples of that window, the same size. So the length of the window will be NFFT. We can still have the freedom of choosing, the size of the window and its corresponding NFFT. So one important term to also notice is that we can have long windows or short windows, and the term used in engineering is narrow band versus wide band analysis. What that means is that if we use long time windows, we get a very fine frequency resolution. That's where we have a narrow band in frequency. If we have very short windows, our frequency resolution is poor, and it's called a wide band. So visually, it's actually quite evident that we can have a narrow band, which means we took long windows in time, and you got a lot of resolution and frequencies. You can see the actual partials. Okay, I cannot play media. I did find that file. Okay, this is a system like I'll try to make up for the missing sound files. Maybe some of it. I don't know if you can hear it. I don't remember if I shared it with the sounds. I'll play it, but if not, I can repeat this in the question section. So this is the sound. You can hear the notes. You can see also the different vowels, which are these little areas, these big, well, I said little areas. These are like these smearings. Okay, maybe they're fast in time, but they're like these smeared areas of different energy changes. And we'll talk about them when we talk about speech. These are kind of what's so-called formants, and they capture actually the content of the speech, you know, the vowels. So we can see the notes. We can maybe read out what Susan Vega is singing. If we do the same analysis with a wideband, okay, which means I took the same frequency analysis. The NFFT is 512 in both, just to make sure that they're kind of the same size of matrices here, and that this one looks smooth. But I took a much shorter window. So we actually having windows of 64 samples. We have many more analysis windows here. What we lose is the frequency resolution. We don't see the partials anymore. We do see much more in detail, or much more contrast, that these little kind of smearings, or you know, high energy, low energy regions, or what we'll call again the formants, which we didn't cover right now. Are these the same? Is this the same signal? Yes. Are these both invertible? If you have the phase, yes, you can perfectly reconstruct it back. The reason I'm a little bit devoting time to discuss about this, the narrowband versus wideband, is that if we do not have the phase, these pictures are very different. And if we apply some algorithms later on, like the Griffith limb, to synthetically reconstruct the phase, what these algorithms will do, they will kind of search for some kind of phase continuity over time. Okay, it will start from a random phase and will try to make up the phase for each one of these FFTs. So each vector here is an FFT. It will try to make up for the lack of phase by creating some kind of synthetic phase and then applying an inverse analysis, but it will also take into account the next frame. And by doing this, you know, if you look at the narrowband, if you look at the narrowband analysis, you can see how the frequencies change, and you can do something about the phase. If you take this kind of analysis and you apply these algorithms, just by the fact that they try to look for continuity over time, in frequency, here you don't have enough frequency resolution to actually do a good job in recreating phase. So even though these aspects are, and you know, the phase reconstruction, the Griffith limb, or even the more advanced methods that people use today in tachotron, in wave-glow, and some other speech synthesis, deep neural networks, there is an element there, which is the element of what they call the vocoder, that takes a spectrogram and creates a sound out of it. That chunk of code that deals with inverting a spectrogram, you know, some of it, or one of the basic methods is just Griffith limb. They didn't really mention that there is an assumption about certain frequency analysis type of a certain resolution in time and frequency that actually allows the Griffith limb to work. If you try kind of now to use shorter windows or longer windows, that immediately will affect your ability to reconstruct your sound from the spectrogram. And you know, I know that it might not make much sense until you hit that issue, but just keep in mind that you know, both in terms of visualization, narrowband versus wideband look very different. If you have not only the amplitudes, but you have also the phases, you can perfectly reconstruct the signal from both types of analysis. But if you neglect the phase, there are remedies. These remedies try to create some kind of synthetic phase that takes into account how the frequencies behave over time. But it does assume, or for these methods to work, you need to have sufficient frequency resolution. Okay, so it has to be sufficiently narrow band to be able to reconstruct the phases. And if you use the wrong frequency setting, or your analysis is too much of a wideband, you will have problem of creating some kind of a synthetic phase and inverting the spectrogram. I think that pretty much ends it. So I will stop the recording and answer some questions.